let's talk about the physical framework that's helping produce the beaches that we're so interested in. In particular, we want to talk about some of the forces that are way beyond the beach. So we're going to talk about ocean circulation, tides, wave dynamics, that stuff today. Now, the lieutenant is confused by all these different landforms he sees along our coasts, and he's trying to figure out, hey man, how is it that we can get all these different coastlines, these different shapes? What's going on here? What's controlling this stuff? And so he immediately figures out that we have three prime suspects. We have ocean circulation, we have tides, and we have waves. Now, before we go on, we just got to say that the lieutenant's had a hard couple days, a little bit ridden hard, put away wet, a little bit paunchy, a little bit unshaven, but we're still going to attack this mystery with all our might. So these three things, these three elements going on here. Hypothesis that they each work somewhat differently. They each are affecting different scales of our planet, and they're each going to impact our beaches potentially. At least that's the hypothesis, but do so in different ways. So let's take a look at each of these things. First, let's look at that global circulation. Now, there's a whole bunch of different flavors of this. We could spend weeks talking about all the cool aspects of this, but suffice it to say, we have a lot of circulation that goes on around our globe. So, for example, on the left, we have this big, giant so-called conveyor belt where we're moving warm water and cold water up, down, all around the world's ocean basins. In general, if we look on the right, we tend to see warm water generally goes from the equator. We're talking about surface water now. Surface warm water generally goes towards the poles, and then water at the poles tends to be cold, tends to be denser, tends to sink, and that's going to tend to move cold water down towards the equator and oftentimes below the surface. So we have all these kinds of things going on, and they create some pretty neat complexities. One of the ways we can track this, if we're talking about just the surface currents, just the moving around of water and energy at the very most skin of the ocean. A neat experiment, natural experiment, if we can call it natural experiment, accidental experiment is perhaps a better phrase, happened starting in 1992. So we had some toys for Christmas and other things manufactured in China being shipped over to North America, and on the way over, storm hit. The ship spilled some of its containers. Some of the containers ripped open and loosed their material into the ocean. This is also known as the friendly floaties experiment, or the friendly floaties incident. And that's because there were many things in here, but amongst the stuff were rubber ducks and toys. And so what folks figured out is actually these guys, these ducks, for example, that are floating, that were spilled from this cargo vessel, just right at the surface. So they're floating just like they would in your bathtub. So they're being impacted by the wind, but they're also being impacted by the surface currents. So they're sort of both. So they're essentially a floater, a tracker of what's going on with these water masses. And so we call that something that's fallen off a ship. We call that flotsam. If we threw it off a ship, we'd call it jetsam. But flotsam is something that falls off. And so all this flotsam gets in the ocean, and it turns out by following where these things landed on different beaches around the world, we could actually track the currents. And so that's what researchers did. So they noticed that initially a lot of the ducks went up to Alaska, then they went up into the Arctic, and then they came down around Greenland, and they hit the East Coast, and they eventually go over to Europe, over several decades. So pretty cool, a pretty neat natural experiment. Now, that's with toys, but we now have incredible tools, satellite-based tools, remote floating objects that can transmit their position through GPS satellite data, all this kind of cool stuff. And when we take all that together, we can synthesize a really complex, accurate picture of how currents are moving around the global ocean. And so let's look at this cool video from NASA that actually goes into fantastic detail of this exact story.
The oceans. They are always on the move. Together, the ocean basins are like a big interconnected highway that transports nutrients, carbon, and heat around the world. This mesmerizing data visualization of ocean currents was created using a model called Estimating the Circulation and Climate of the Ocean, or ECHO for short. It's built using real-world data from satellites, buoys, and all kinds of other measurements. All of this movement starts with physics. Because the Earth is spinning, the water feels something called the Coriolis effect. This pushes some of the strongest currents, like the Gulf Stream and the East Australian Current, against the east side of the continents. Because these currents wind up on the west side of the ocean basins they sit in, scientists call them western boundary currents. In this visualization, the currents closer to the surface are white, and the deeper currents are blue, almost like you're seeing those deep currents through the top layer of water. But what's causing all this motion? And what makes some water rise and some water sink? Let's take a look. Here we can see the Pacific Ocean's strongest current, the Kuroshio. It begins in the warm tropical Philippine Sea and then flows north past Taiwan. After it reaches Japan, it turns east and heads across the Pacific Ocean, spinning off huge eddies where it turns right. The Kuroshio carries over 200 times more water than the world's largest river, the Amazon. This visualization makes it easy to see how the ocean moves water across the planet. But what's hard to see are the places where the water moves up or down. This is called upwelling or downwelling. When upwelling brings cold, deep nutrients into the sunlight near the surface, it creates a feeding ground for all sorts of ocean life. Nutrients, carried in part by the Kuroshio current, help feed the fisheries in Japan and create an important economic zone for the country. Another major western boundary current is the Agulhas Current, which carries water down the east coast of Africa to its southern tip, called Cape Agulhas. There, the current makes a sharp turn to the east, but sometimes it pinches off giant eddies called Agulhas rings, which drift west into the Atlantic. These circular currents carry salt and heat into the Atlantic and form an important part of the overturning circulation, also known as the global ocean conveyor belt. This so-called conveyor belt is a system of currents that carries heat northward across the equator and into the North Atlantic. It plays a big role in the climates of North America, Europe, and Africa. Without it, winters in Europe would be much colder and droughts in Africa more severe. But the oceans do more than just move heat around. In some places, they absorb heat from the sun, and in others, they release it back to the air. We can see that in the Gulf Stream. Yet another part of the ocean's conveyor belt, the Gulf Stream starts in the tropics, where the water is very warm. As it drags warm water up the east coast of North America, it acts like a heater for the atmosphere. By the time this water has wandered across the Atlantic and wrapped around Europe, Iceland, and Greenland, it's gotten so cold that it sinks deep into the North Atlantic Ocean. But temperature isn't the only thing that can make water sink. So can salt. Salinity, or the amount of salt in the water, can make it heavy. The saltier and colder water is, the heavier it gets. As it gets warm and fresh, water gets lighter. Changes in the heaviness or density of ocean water are what keep the ocean's conveyor belt turning. The streaks you see near the surface show how water is moving from one place to another, but if you look closely, you can see that deep down, water is moving in a different direction, sometimes even the opposite direction, like it does far below the Gulf Stream. This cold, deep water headed south beneath the Gulf Stream is another part of that same ocean conveyor belt that keeps Europe warm. Some of that warm Gulf Stream water that heads north at the surface eventually winds up there, moving south again after losing so much heat to the atmosphere. Eventually, this cold, deep water will spread around the globe and slowly rise toward the surface. There, it will warm up in the sun and get ready to start the trip all over again.
So, all of that cool stuff is the starter lens, the overall picture that's going to be moving water masses around our planet and delivering energy, etc., around our planet. So this is a summary of the surface currents, the most common large-scale currents that we see around these basins, and you can see that they're pretty much within different oceanic basins in different parts of the world, but there is some similarity in how these things move around. Okay, so that's the first thing, is we have this large scale energy movement around the planet driven by wind and temperature differences and salinity and all this cool magical dance. The next thing is we have tides. So the interesting thing about this is we have to realize that the Earth is basically rock, and the ocean is a liquid on top of that rock that's associated with that rock, but it's not actually affixed. It's not actually attached to that rock. So while the rock can move underneath it, the liquid has some independence. That's the key thing. And so what we need to know about here is position of the Earth, position of the moon, position of the sun. And the relative positions of these things are going to either act to stretch out, pull, extend water farther from the rock and make it bulge out, essentially, or make it not bulge out and be more contained and close to that rock mass. So let's look at a couple of illustrations to make this point. Now, the first part of this is the fact that the moon and the Earth are exerting gravitational pull upon each other. So here on the Earth, the moon's gravitational pull is going to cause the oceans to bulge out on both sides. The sides closest to the moon and the side farthest from the moon. And these bulges are essentially high tides. The low points are where we have low tides. Okay, next, the moon's gravitational pull on the Earth combines with other forces and causes the water to be redistributed, and ultimately makes the bulges of water on the side closest to the moon and the side farthest from the moon consistently. Okay, next, we are spinning. The Earth is spinning around, as illustrated by this person standing on the Earth. And the rising and the ebbing, or the increasing and the shrinking tides, happen as the Earth's land masses are going to rotate through this bulged water, these tidal bulges created by that the moon's gravitational pull. So our observer there that's on the Earth is going to see the tides rise when we pass through the bulges, and it's going to look like the tides are going to fall when we pass through the low points. Now, of course, the Earth isn't a perfectly smooth ball. We're more like a squished orange. So tides are also going to be affected by the presence of continents, the local shape of the Earth, the depth of the ocean in different locations, and so on and so forth. So the timing and the height of the tide near us is going to be affected by all those various complex elements. Next, what we're going to see is twice a month, when the Earth and the sun and the moon are lined up, their gravitational power is going to combine to make exceptionally high tides. We call those spring tides, as well as very low tides where the water gets displaced. When the sun is at a right angle to the moon, we're getting those moderate tides, what we call the neap tides. And from our view on the Earth, these tides coincide with the appearance of the moon, the different lunar phases, as we go from full moon to waxing, waning, all that kind of good stuff. So finally, the Earth's tidal bulges don't exactly line up with the moon's position, that they mostly do. But because the moon is orbiting in the same direction as the Earth rotates, it takes extra time for any one point on our planet to rotate and reach exactly below the moon. This means that the high tide bulges are never really directly, exactly, perfectly in sync with the moon, but they're a little ahead of it. So that's tides. Now, in a practical sense, when we talk about, hey, how high is the tide here? What we did for many centuries was actually mark on a rock or a wall, or in fact go out with a ruler. And that's what the lieutenant is doing here now. He's going out to the coast, he's putting a ruler down, and he's measuring how high the water is at any given point. And he's going to do this every day. He's going to do this all over, and he's going to measure the water line at different times, and he's going to document that and begin to understand what the tidal range is like on our particular part of the coast. Now we have three different flavors of tides around the planet, three main different flavors. Before I get that, though, let me first tell you that this next part is we're going to hunt for the water line, the exact line where the water is going to strike the coast consistently. Now, obviously the tide's going up, tide's going down, but we need some line. We get that it's a dynamic system, we get that it's going up and down, but we need something to use as a basis for planning, for where we put our roads, where we put our pipelines, where we put our houses, all that kind of stuff. So we need something. And so that something is what we might call the water line. Now we can generate this in a bunch of different ways, but mean higher high water is the typical way we do that. Now I'll put a pause on that real quick. Let's turn and look off to the left. Let's look at these three different categories of our types of tides we see around the planet. The top, we have what are known as semidiurnal tides. The bottom, we have what's known as diurnal tides. In a diurnal tide, we have one high tide and one low tide each day. In a semidiurnal tide, we have two high tides in a day and two low tides in a typical day. The one in the middle, though, is the most important one. The one in the middle is what we have here in California and what most of the planet has most of the time. So we call these a mixed semidiurnal tide. So it means that, yes, we have two high tides and two low tides each day, but of those high tides, one is a higher high tide and one's a lower high tide. And with the low tide of the day, low tides of the day, there's going to be one that's a higher low tide and one that's a lower low tide. And that's what the lieutenant was measuring when he went out there. When he went out there and let's say measured the highest point that we saw on a given day on his ruler. So when we do that long term, when the lieutenant goes out and does that for days and days and days and months and months and months and years and years and years and decades and decades and decades, we eventually can calculate where that water line is. And while we could do this in many different ways, the most common one is to use the mean higher high water. So to average the mean higher high water on a particular location. And that is what we typically use to define the shoreline, the water line. And that's how we know about our tides. Obviously, we used to go measure this all the time. Now we have these fantastic satellites, all kinds of wonderful automated sensors, and really robust mathematical models that will describe for us the tides at different points around the Earth, different geographic locations, different times of the year, etc. So what we can get from this is a so-called tide chart. So here's an example of a tide chart from June for the coastline near the city of Ventura. And what you see is, again, we have that mixed semidiurnal tide. We have a higher high and a lower high. We have two high tides, two low tides, etc. And you can use this for planning. You use this to plan your surf trip. You can use this to plan your trip to the beach. All that kind of activity is made possible through the fantastic research and monitoring that we've done over the centuries and the science that we put into understanding how tides work. It's also important to say that while I just was describing the typical situation, say on a Southern California beach, it is true that tides are going to vary, as I mentioned before, based on a bunch of different things. So local geography matters, etc. So if we talk about how high the tides can get, etc., it's going to vary around the planet. So explaining all the details is a bit beyond us in this particular survey class, but I just want you to understand that not all of the Earth is experiencing the same tide at the same time of the day. Even the same latitude is not experiencing the same thing. And it's also important for you to understand that even though we're here in California, we have some places that are even much more extreme than we are. So, we might see a 4 or 5 foot tidal range, in a typical tidal cycle, or not typical, but it may be an extreme tidal cycle. But that is nothing compared to the craziest place on Earth for tides, which is the Bay of Fundy up in Canada. And because of the geography of this bay, it acts like a funnel. It really, really amplifies the tide when the tide comes in, and it really over-exaggerates the leaving of the tides when the tides leave. And so if you go to the Bay of Fundy, what you'll see in the high tide, like on the left here, is you'll see boats tied up at dock. They're looks like any old regular seaside port. However, when the tides go out, basically much of the bay is simply mudflat, massive mudflat for miles and miles and miles. And so the boats actually come to rest on the mud. It's pretty nuts. It's pretty crazy if you ever get a chance to go up there. And so we're talking on the order of one tidal, one series from a high to a low could be as much as, 40 or more feet. So 16 meters or so. Pretty darn amazing. Now, what I've just been describing to you are the regular tides. We do have a couple other types of tides that we need to mention. The first are king tides. Now, king tides are the highest tides of the season. So if we're going to have a high tide, anyway, and we move into a time of the month where we have really strong pull of the moon and the sun, we can get pretty strong, pretty extreme tides. And these, they're in and of themselves, they're a challenge, but what we oftentimes talk about them being useful for now is forecasting the future. So this is higher than normal tide, but because of sea level rise, this really is a snapshot into what our coasts will look like in a few decades. Given the ocean is rising around. So they're quite useful. So what does that look like? Well, here's a little example of some king tides on PCH. So this is by Thornhill Broom, and this is me driving in my car last year. And so you see the water is breaking over and onto the roadbed. Now, if this king tide were to become more the normal situation, we'd either have to abandon this part of PCH or add a lot more protection off to the side or raise the roadbed, because that level of constant washover is going to destroy the road, erode the base of the road, and then eventually take out the asphalt itself. Okay, those king tides. Okay, lastly, our third thing are waves. Let's talk about waves. Now, we have a bunch of different types of waves. All kinds of cool aspects are here. We won't be talking about all these. We're not going to talk about electromagnetic waves. We're not going to talk about the way wave energy propagates through a spring, so-called longitudinal waves. The type of waves that matter for us in our beach explorations are these two that are left over. So the first are transverse waves. And that's illustrated here. So transverse waves, so what I'm showing you with this animation is the energy is moving from the left to the right. So the wave is propagating from the left to the right. And what I'm showing you here with all these little black dots, those are all pieces of the material, pieces of the matrix. It could be air, it could be water, whatever. And so while the energy is going from left to right, the particles, the molecules, are actually not moving for the most part. They're going up and they're going down. They're moving perpendicular to the direction of the energy propagation. And so you can see that, or you can illustrate that if we take a rope and tie it to a door handle and just start like, kicking our wrists and flicking it up and down, and the rope kind of makes these waves undulating down. So the energy is propagating down the rope from your hand, but the rope is not moving closer to the door. I'm holding onto the rope, or the lieutenant here is holding onto the rope. And so the molecules of the rope are going up, going down, but they're not moving closer to the door. So again, that's a mechanical wave. That's a transverse wave. And that happens inside the ocean. Next, we can talk about waves that are at the interface of two media. So in our case, we're going to talk about the interface between the air and the water. So surface waves. So here, another illustration. Again, each of the little dots represents a molecule of water. And so again, the wave is moving from the left to the right. So the energy is going from the left to the right. But have a look at the guys at the surface. And so if you focus on that one little orange molecule, it's going up and down, but it's not just standing exactly going up and down, in a vertical movement. It's tracing a circle. So it's going a little bit forward and then falling backwards, and a little bit up and a little bit down. And so it's tracing that circular path. And that is a surface wave. Now, if you and I are scuba diving, we put our scuba tanks on, we go on the surface of the ocean, we might sit there and, you might start to get motion sickness, because we'll be floating on the surface of the ocean, and we'll be bobbing up and bobbing down and bobbing up and bobbing down. If you're prone to motion sickness, that won't feel good. So if we're sitting there and we're talking, you start to say, "Hey, Dr. Ray, I don't feel good." Well, I'll be like, "Great, just put your regulator in your mouth, and we're going to go down." So we're going to start breathing underwater, go down, and we're going to go a certain number of feet, depends on where we are and what ocean, but we go down a certain number of feet, and we don't feel as much movement. We go down a little bit deeper, below the so-called base of the wave, and we don't move up or down. So we're no longer moving in that bobbing cork-like motion that we were at the surface. So that is a property of ocean waves, surface waves. And if we now extend that analogy and continue on, this explains what's going on our shorelines. So again, on the right-hand area over here, where we have these circles, here we have that typical the water molecules moving up, down in a circular pattern, etc. Eventually, when we get to, and here's the wavelength, I'll define that for you in a minute, but basically how wide the wave tops are from each other. The bottom here, the base, will be 1/2 the distance of between the two tops of these waves. So we have surface waves, and once we get in here, these behave like regular waves that are not at the surface. As we move, and so that's in the open ocean. As we move towards the beach, we're going to start to get into some different situations. The first thing we're going to do is we're going to get to the situation where the bottom of the wave, the base of the wave, is striking the ground. And so in that case, what we tend to get, instead of getting circular motion of the water molecules, they get more ovoid. They get more sort of flat and squished. And then as we continue on even further, as we get to 1/20th the wavelength, then we actually start to get the water piling up, and it doesn't behave in this ideal fashion. It starts to fall on itself and fall over, and we perceive that as waves. We perceive that as the classic wave breaking on the ocean. So in that case, the water molecules are flopping around and are getting moved around and are not just going up, down, right, left. They're going whoosh and tumbling, bumbling everywhere. Okay, so a couple of those parts of the waves that I want you guys to know about. Let me run through them. So here we have the waves going up, the wave going up, the wave going down, etc. The bottom, the lowest part of the wave, we refer to as the trough. The highest point of the wave we refer to as the crest. And the difference between the crest and the trough is the so-called wave height. If we were out there surfing or swimming out in the ocean, we tend to be at the average depth, and we look and we tend to say, oh my gosh, that wave's about a foot tall or so. Really, the wave height is the difference between the highest point and the trough. So if we're out there in the water, we oftentimes underestimate the actual wave height because we are floating in it. Okay, the next thing is we can pick any position. Usually we pick the top of the wave, but it could be any consistent position. So the top of one wave to the top of the next wave is known as the wave length. And then if we start our stopwatch, if we're say at the pier and we see this one wave, rise of the water right there, and we start our stopwatch and we wait for the next time the water rises, that time is known as the wave period. And so the faster the waves are coming in, the shorter the period. As these waves move towards shore, they're generally speaking coming from far away. They're the product of wind and all this energy far away from land. And so the waves tend to move in large, broad, parallel waves of energy. As they're coming in, they begin to hit the local geography of the coast, and that's where we tend to get differences. We tend to get so-called refraction or bending of the waves. So what were originally parallel waves start to get curvy and sloppy. And so headlands tend to get a lot of focus, a lot of wave energy. They tend to get a lot of erosive energy. Areas that are behind those headlands, like say a bay, tends to have that wave energy dissipate and spread out. And so therefore it's not as energetic, it's not as erosive on this part of the coast. And so we tend to have nice big beaches in the back of bays because of that. And we tend to not have many beaches on headlands because of that. Same thing, just another illustration where we have waves bending around and responding to the topography, the landforms of the shore, and therefore the amount of energy is either concentrated or dissipated in response to how they are refracted around these different structures. Okay, the last thing is this stuff is going to pull us together to start to add these different forces together. We can start to add in these currents along with the tides, along with these waves, and then we can add some extra spice on here. So for example, we can add a storm, a hurricane, that's going to add even more energy, even more wind, and so tend to produce what we often see as very destructive, very powerful events that we refer to as storm surge. Now, storm surge is not just a bang, bang, in and out. Storm surge is a oftentimes many hour long increase in the height of the ocean, and they are very problematic and they are very destructive. So let's take a look at an illustration of this. And so in this case, this is the first time this was visualized this way. So it's kind of a classic video here by these folks at the Weather Channel. And they're trying to communicate to folks before a hurricane arrives what it's actually going to be like. And until you've experienced a storm surge, you don't get it. You think it's going to be like a regular wave. It's going to wash in and wash back. No. So let's watch this video.
Extremely dangerous Hurricane Florence continues to close in on the southeastern United States, and it will carry with it significant storm surge and life-threatening inundation. Let's look at these maps, for example, created by the National Hurricane Center to give us almost a block-by-block assessment of how much water rise you can expect above normally dry ground. This, for example, over southeastern North Carolina in Beaufort and Morehead City. These are some locations that we think will get significant storm surge. Now, these areas shaded in yellow and orange can expect water rises of 6, maybe even 9 feet. That's going to flood many of these locations downtown. But it's more than that, because this is not just going to be a coastal phenomenon. We know that the storm surge with Florence is going to continue inland and surge many miles. For example, in Newport, North Carolina, significant inundation, water rises above 9 feet nearby, and even farther west than that, this storm surge will find its way well inland. So let's now have a look at what that might be like. For example, we know Florence is going to bring 1 to 3 feet of inundation across many locations. That certainly is enough to knock you off your feet. It can definitely stall cars out and even carry cars away, and certainly flood many of the lower levels of structures. But we know Florence is also going to bring water rises well above that, perhaps up to 6 feet. Now, 6 feet of water, imagine that. That carries large objects in it, like cars, for example, that can act like battering rams and enhance the damage that would otherwise be. And also, we know that can flood the lower levels of many structures. We also know that Florence is going to carry with it likely storm surge well above that, perhaps 9, 10 feet, maybe more. That will totally cover up one-story buildings and structures, leaving them underwater, and certainly pose a risk to many. There are very few places that are safe when the water rises this high. So please, follow the advice of your local officials and heed the evacuation warnings, and of course, stay updated on all the latest forecasts.
So what we can see there is the storm surge really is a massive rising of the sea. It's not, it's the surge has been a surge of water moving in front of, in this case, the hurricane, but it is pretty devastating. Even if we don't have that large a storm surge, even relatively modest storm surge can have huge impact. So for example, this road here has been eroded. The bottom of the cliff has been pounded away by the storm surge and has eroded it, and now it's taken part of the roadbed out. We also see crazy elevations of water and huge pounding, water moving higher and farther inland during a tsunami. And so in this case, this is the tsunami, the 2004 tsunami, in this case in Thailand, where the surface of the ocean just got super high in the wake of this earthquake and is propagating inland and is killed a lot of folks. And here is the we think of the Fukushima disaster when we think of the events in Japan in 2011, but really it was an earthquake that led to a tsunami, and the tsunami moving inland is what actually damaged the nuclear reactor that led to the radiation release. What we're looking at here is a pretty incredible photo. This was taken by folks that were on a parking garage, a multi-story parking garage. The thing here that looks like a rapid, that's actually a flood wall that was erected to protect the town decades ago. So it was like over 30 feet tall. And that was designed to keep, storms just like this, tsunamis just like this, giant rises of the ocean just like this out of the town. It did not work. It was not high enough. And you can see that water now pouring over it. The whole surface of the ocean has risen up. So it looks like we're a river, but in fact, this is a temporary elevation of the ocean's surface, and you can see it carrying away those trucks and cars and everything. It's quite devastating. Okay, so with that now, we have our currents that are going on around the planet. We have our tides that are going on around the planet and actually playing up on our local beaches as well. And then we have the waves that are delivering that actual energy right onto our beaches that are providing erosive forces, etc. And so with this, so we've solved it. And so with this physical framework solved, we can turn to investigate how these forces are going to combine to impact sediment. And so we've gone from having these suspects to now we know they're not suspects, we know they're actually culprits. So these are key forces in shaping our beaches. Good job, Lieutenant. He still looks a little ragged, that guy. So real briefly, by way of summary, today we just mentioned large-scale physical processes. We talked about ocean circulation, which is operating at the large scale. We talked about tides. We here in California, as with most of the world, have so-called mixed semidiurnal tides. Those tides are going to dictate water level, and therefore much of the erosional framework that's going to happen along our beaches. And then waves are going to come in and actually do the actual moving around of the sand, and both being impacted by landforms and in turn shaping landforms on and around our beaches.